thank you. Thank you very much for being here. You guys have no idea what it means to me to be here today. Really, I'm having a big day, right? And I'm very grateful to be able to share this day with all of you. So before we begin, let's go over the contents. This way you know what you're getting yourselves into. So I have a couple of slides based on motivation. I think that this is a very important part because if you understand why it is that we chose to do such a simplified approach for the entire set of research, then you will understand better the decisions that we make for each one of the chapters. After this, I'm going to focus on each one of the 4 main chapters of the thesis. So, as you can imagine, I have like 28 minutes to summarize 4 years of work, so I'm going to have to be very shallow into each one of these chapters. I'm only going to focus on the whys, the hows, and the whats. But each one of these chapters is also related to a publication, which is already out, or is going to be soon out. It's in publishing. So there are more resources around if you're interested. Finally, I have a section for future developments. I don't have conclusions at the end. I'm going to be providing conclusions for each one of the chapters as they start coming along. I think that makes more sense. So, for motivations, how did we get here and why did we choose to try to do something about this problem? So my motivation is basically related to my own experience in a couple of research projects that I worked for my first 2 years. So basically there was Iterate and there was Infinite. They were both regional risk projects. The specifics of the projects are not important right now. What is important is that I noticed that even though there's this big body of research that has to do, with like the state of the art of how to do risk assessment, when you actually have to sit down from the practitioner side and start to work on it, you have limited time, limited resources, limited information, and in the end it doesn't add up. So what we decided to set as a goal was, okay, let's do something to provide useful contributions to the application of this type of problem, regional risk assessment of bridge portfolios. What I'm basically saying is, there's the state of the art and there's the standard of practice. So instead of me focusing my PhD on trying to extend the state of the art, I'm going to try to do something to bridge the gap, like to try to make things a bit more approachable. So we defined some research questions. Basically, we have 4 research questions, 1 for each one of the chapters. The idea was that we were going to have 1 for hazard, 1 for exposure, 1 for vulnerability, thus covering risk, and then 1 final one that kind of sums everything up into a decision-making perspective. Now, each one of these questions could be applied to buildings as well. So why did we choose bridges? So this is basically the issue. In this slide that you're looking at is collapses in Italy that have happened for bridges in recent years. Now, in this slide alone, you have billions of euros in losses, and you have 48 casualties related to this slide alone. So we said this is a problem that is only going to get worse. So it's kind of a problem that's worth taking a look at, trying to do something about it. So, chapter 1, for the hazard. For the hazard component, we wanted to do an evaluation of intensity measures, basically trying to answer the question, which one is an efficient intensity measure to use for this type of problem? So why did we choose to do this is that there are different choices about intensity measures. There's a lot of different decisions that you can do, and there's a lot of different intensity measures that you can choose. By far, the most famous ones have to do with response spectrum. So if you look over here, there's like this example of a response spectrum for accelerations. Over here, you will have PGA. Now, this is the legacy intensity measure. This is the most famous one. This is the one that everybody thinks about. The thing with PGA is that in recent decades, it has been proven to be a bad predictor of performance. So we need to start looking for other options. Another very famous one is spectral acceleration in 1 second. This one makes sense in the case of buildings. If you have a building which is regular with a very strong first mode response, that first mode happened to be around 1 second, then yes, you're going to have it will be a good experience to use spectral acceleration in 1 second. However, for bridges, this is rarely the case. Since bridges have this horizontal configuration, you usually have a whole set of periods which are going to have like enough spectral content that is going to be important for that bridge. Now, this is only talking about one specific element. If you want to talk about a portfolio, the situation gets worse. You have a whole lot of periods. So for this type of situation, you might want to start considering about a range of periods. And this is where average SA comes in. So average SA is basically a kind of mu intensity measure. It's about 7 years old, 8 years old, which tries to take within a period of, a range of periods of interest is going to average out the response. In the last recent years, there's been a lot of buzz about average SA being like the ideal intensity measure to use for this type of problem, but we thought that it hadn't been really evaluated in a large case study of real existing bridges. So that's exactly what we did. So what we did was, okay, let's test. Average SA against PGA, taking it as the biggest contender, in a large inventory of real bridges. What we did for this, so we have a database of 400 real bridges that exist in Italy with full information. We had like blueprints for this ones. And we defined a site for hazard in the region of Campania. We combined the two, so we took a subset of 165 bridges and located it around the hazard site, in locations where real bridges exist around the hazard site. And so I created a case study. That would be my synthetic case study. Once I have this defined, I run my hazard package to speak. So I perform conditional record selection for both PGA and average SA. 9 return periods, 30 records per period. I go into a numerical modeling campaign and nonlinear time history campaign all the way so that I can get fragility curves for each one of the assets in my inventory. So over here you're looking for fragility curves for each one of the assets, 165 for both PGA at the top and average SA at the bottom. Once that we have these results, then we start the comparison. So the first metric that we decided to use was dispersion in the fragility curves. You probably cannot see it very well over there with this monitor. I can't see anything. But basically what we found was that average SA does lead to lower dispersion values for the fragility curves for both limit states that we evaluated and for every single asset in the inventory. Another thing that we wanted to evaluate was what about the dispersion in the response. So we have from the nonlinear time history campaign a database of demand over capacity ratios. So what you're looking at here is for both the damage and collapse limit state. Average SA is in red at the bottom, PGA is blue at the top. So consistently, average SA will lead you to lower dispersion in the behavior for all of the return periods that we evaluate. This will of course lead you to lower probabilities of exceedance for each one of the return periods, and therefore it's going to lead to lower average annual losses calculated. So for average SA, we found for the overall of the inventory a 0.4% of average annual loss. And for PGA, we found a 0.5%. Now this sound like small numbers, but the difference between them is in the range of 20 to 25%. So really, like, the difference is significant. Finally, we decided to run a scenario so that we could see what happened in terms of interruptions. We defined a threshold. So if any of the bridges go above the 30% threshold of collapse limit state or 50% of damage, then we're going to flag it as interrupted. So basically we find for PGA 72 interrupted bridges, for average SA 59 interrupted bridges. So, in conclusion, average SA does seem to be more efficient than PGA, at least based on the lower dispersion that we get in the values of fragility curves, consistently lower dispersion in response, and therefore lower probabilities of exceedance, and non-negligible effect in losses and interruptions. Okay, so chapter 2, exposure. This is a nice one. I really like this one. So for this, we wanted to evaluate the effect of how much knowledge of the exposure you need to have for your results to make sense. So why did we choose this is that the reason why I say that this is a big one is because this happens all the time, right? When you're trying to deal with this type of projects, having full knowledge of your inventory, it's very rare. It never happens. Typically what's going to happen is that you're going to have full knowledge on a specific portion of the inventory, but then you're going to have another portion of the inventory for which you have no information or very little information. The way that people deal with this type of thing is that, okay, you take the information that you do have and you make the full calculations and you calculate your fragility curves like the ones that I just did, and then we use a taxonomy-based approach. So basically, with the ones that I do have, I'm going to create a median curve, and then I'm going to backpropagate this median curve to all of the assets for which I have no information. Disclaimer, this would of course assume that all of the bridges are in the same taxonomy branch, which would not be true. This is a slide made for educational purposes, right? So just keep that in mind. So we decided to test this out because depending on the percentage of the information that you do have, of course this is going to have some effect on your results, right? If I only build my taxonomy base with 10%, it's different than if I build them with 80%, right? You can see how that might be an issue. So we decided to evaluate this type of situation. So how we did this is that, again, we build a case study with full information. So I take my 400 bridges for which I have full information, I apply a taxonomy scheme, and I classify them into each one of their taxonomy branches. In this case, we chose the region of Salerno as the case study region. The region of Salerno, we took out the road network of the region of Salerno. It has 620 bridges, and we started a sampling process. So I take bridges from my database, and I start putting them in locations where there are bridges in the region of Salerno. Once I'm finished, this is a synthetic case study, and this is going to be a synthetic case study with full information. For generalization purposes, I did this 10 times. So I have 10 very slightly different configurations of the same case study with just different bridges in different locations. Once that I have this defined, I run my hazard package, I define the average SA range that suits me for this type of problem. I get hazard curves for each one of the sites, and I perform record selection again. Again, 9 return periods, 30 records per period. Once that I do this, I run my vulnerability package, right? I do my nonlinear time history analysis, and I obtain my results. What you're looking at here is results for each one of the fragility curves, for each one of the 620 elements in my inventory, divided by taxonomy branch. So once that I have this, I can calculate losses. Now, for each one of the different 10 case studies, I'm going to have different values of losses. In average, they're in the range of 2.5 million. This is aggregated average annual losses for the entire region of Salerno. Now, these results have uncertainty, but that uncertainty is not coming from the exposure component because it has full information. I have all of the information that I want to know from here. So then once that we have this and we use this as a benchmark, then we decide, okay, how about if I start removing information for myself? I go back to the original part of the problem, and then I start hiding information for myself. And I can rerun the analysis, repeating with my taxonomy-based approach, and compare the result that I would get with the taxonomy base with the baseline that we have from before. So to do this, let's say I want to sample 40% of the exposure. Depending on the 60% that I hide for myself, I might get different responses, right? And I never know which ones I'm picking when I'm in a real-life situation. So what we decided to do, again for generalization, is another sampling process. In the end, for each one of the 10 case studies, we have 20 exposure ratios that we wanted to evaluate, 5, 10, 15, 20, all the way up to 100, and 40 samples for each one of those exposure ratios. So you're looking here at 8,000 points. Statistically, it looks like this. So here's where the results come. This is interesting. So in median terms, the taxonomy-based approach will lead you to slight over-prediction. This is not a property of the taxonomy base. It could have been an under-prediction as well. It's just a property of the case study. What is important to notice is that even for low values of exposure ratio, you are going to have a very, let's say, controlled response in median terms. You have a maximum of 8% of the difference between the baseline and the median one. What also you can see over there, I hope that you can see it over there, is that there is a big dispersion at the beginning that has it reduces with a nonlinear trend, right? So this will lead you to two things. Okay, if you have very low exposure percentage, you will have a lot of uncertainty. But if you're at 10%, if you increase to 20%, you're going to have a huge reduction in uncertainty. So that's worth the money. If you're at 50% or 60%, if you already increase 10% more to 70%, that's not going to lead you to a great reduction in your uncertainty. So this is information that you can use. This is for taxonomy base. Finally, we said, okay, as a small bonus, how about if we use machine learning to include more parameters into this? Instead of using the same taxonomy-based curve for all of the elements for which I don't know, I can build a database with my nonlinear time history results and use this database to train a machine learning model and try to assign a different curve to each one of the assets for which I don't have any information. Now I know that you're probably not going to see very well the results over there, but we repeated, with a random forest algorithm. We use 6 features that are very easy to get from, let's say, remote sensing information. What we find is that after the 20% mark, you have enough information to train the model well enough so that it outperforms the taxonomy-based curves. Also, in median terms, it stabilizes a lot easier. So after the 20% mark, it starts working better. It outperforms. In conclusion for this chapter, so taxonomy-based curves can lead to accurate results on the aggregate, right? On an aggregated level. If low percentages of exposure are known, there's potentially a large error, and you do benefit a lot from improving a little bit more on your exposure knowledge. You get diminishing returns when you have a large portion of the inventory, so it's not worth, if you're already at large portions of the inventory, to try to get more. And machine learning models cannot perform taxonomy-based results if you have the time and the knowledge, because they are a lot more difficult to apply. Not that they're difficult, but they are more difficult to apply than the taxonomy-based part. Okay, chapter 3, vulnerability. This was my favorite chapter. It was very much outside of my comfort zone, so I really enjoyed when I got results from this one. So what we wanted to do for vulnerability was try to do something about indirect losses. The reason why is that for several years we have been discussing that the indirect losses in bridges may have a much bigger impact than the direct losses. But we really have been neglecting it. We haven't really started talking about a lot of methodologies or doing this on the regular basis of how to calculate indirect losses. If you look at the consequences of the Morandi Bridge, which is something that there's a lot of information about, the direct losses are in the range of 220 million. The indirect losses, the Chamber of Commerce of Genoa made some estimates, and in medium terms, right, it could be worse, it could be better, but in medium terms they estimate a 2.35 billion euros loss during those 2 years that the bridge wasn't there. So we are talking of a ratio of about 10 to 1 for indirect to direct ones. So this does seem to paint a picture that this is a real problem that we need to start taking care of. So what we decided to do was, how about if we define a methodology that is not going to be better than anything that it's out there, but it's going to be at least less intimidating than what other people have been applying so far. And we're going to purpose it for prioritization, not something specifically for like loss calculation, like really fine loss calculation, but we're just going to go for something for prioritization, something simple. So let's say if you have a network model, this is an idealized network model, so you have A, B, and C, each one is a city. You have lines, which are roads, dots that are intersections, and the weird things in the middle, they're bridges. So you can load this up with information from traffic. You can figure out what is the traffic flow in each one of the places. This will be your baseline model. So this is when everything is operational. Once that you have this, you get aggregated metrics for how the users are spending their time in the network, and you can plug that in with some money to get some baseline operation costs. So this is your baseline. So what we decided to do is, okay, if you want to consider that maybe this bridge has collapsed, then what we do is that we remove it from the model, we rerun everything, we see how the traffic redistributes within the rest of the network, and then we have a modified case study with modified operation costs. So what you do here is that if you take your baseline, you subtract it by the other one, you're going to have something, a monetary value which is at least proportional to the value of indirect losses that you can expect from losing that bridge. So this is what we did. So we took our case study region, we defined the traffic road network, divided it by municipalities, we built our road network model. Everything was done with open source software and information. We took information about traffic from census, and we loaded up in the model, and we have traffic flows for each one of the roads. We get the aggregated metrics of how much time and distance all of the users combined do on a daily basis on the network. We plug this in with some money information, and we end up with something that's a daily baseline cost. So this is my benchmark. After I have this, I do what I just said. I start removing information one by one bridge at a time, recalculating everything, subtracting, and getting a measure of indirect loss. And this is how it looks like. Now, these results are good. The problem is that at this point, they are on a daily basis. This is a daily result because I'm running with daily traffic information. So now the question becomes, how long does it take to replace a bridge? So, sadly in Italy, luckily for me, but sadly in Italy, there is a lot of information about collapses in Italy. So we went over to the news and we started finding, okay, which bridge collapsed, when did it collapse, when did it reopen? We found 10 occurrences and we built our own repair function. So this repair function has a huge uncertainty and it's built only with 10 points, right? It can take anything between 3 months in Torino to 6 years in Sicily to repair a bridge in Italy. So, I mean, it varies a lot, but the good thing was that in median terms, we found 710 days as the replacement time. Now this is roughly 2 years. Makes sense, sounds good. It's almost on point to what the Morandi Bridge took to be replaced. So we decided to just keep it simple, use that same value, the median value, and just apply it to all of the indirect loss daily values that I had from before. And this is how it looks. So this could be a median loss that's associated to the collapse of each one of the bridges. It can be seen as an indirect replacement cost, right? Because this assumes the deterministic collapse of one bridge at a time. So it's kind of an indirect replacement cost if you're comfortable with the concept of replacement cost. And this is very useful for prioritization, right? Because if I can define then a priority based on these values over here that are representative of indirect losses. Now, if you run if you use it as an indirect replacement cost and make the same calculations that you did for your direct ones, you can make a comparison. So to your left, you have direct losses, and to your right, you have the indirect losses that were calculated. So when you aggregate them both, you get very interesting results. So for this case, 9 bridges represent 42% of the total average annual loss for the entire region. Now, this is not true, of course, because those bridges don't exist in those locations. But if it were, if it was true, this would be great for prioritization, right? Because you identify those 9 bridges, you can go take care of them, and then you increase the resilience of the entire region by 42%. That's pretty good. Another thing is that if you compare the direct to indirect losses, we're talking about a 4-to-1 or 5-to-1 ratio of indirect beating direct ones. So it does kind of confirm the suspicion that this is a problem that that it's worth trying to explore. In conclusion, the indirect effects of bridge collapse can be much greater than the direct ones. So this is something that we need to start paying more attention to. The indirect losses depend on traffic demands and redundancy of the network. Now, this is a very obvious conclusion. I say this because it can be a very small road, a very small bridge on a very high traffic road that you might not be paying attention, that if you lose that bridge, you're going to have huge indirect losses. More so than a bridge that you might be paying attention, but it's in the middle of nowhere. So there can be a great concentration of losses and very few assets, and that's always good to know, right? Because if you can identify them, then this is great for prioritization. And this type of analysis is useful for decision makers, so that they can know which assets to prioritize. Finally, so we decided to do something, taking advantage of all of the previous 3 chapters and just trying to do something that felt like a conclusion, right? That felt like I was using all of the information that I had gained from before. We decided to do something about how can we prioritize assets within a portfolio. So why did we choose to do this is because right now, bridge management agencies, they have issues handling their inventories. At this moment, they have a huge inventory of deteriorating bridges for which they have very little information, they have very little resources, and they have no idea where to begin. Doing the full assessment, like the exercise that I've just done, is not always feasible for them because they don't have the resources. Ideally, you could get some type of methodology that is meant only, based only on very simple parameters of each one of the bridges, something that you can find remotely or something that's easily obtainable, that you can find which is the priority for which bridges you have to go and check out first. Now, this situation is something that the Italian government has taken very seriously in recent years. After the collapse of the Morandi Bridge, they started pushing out a lot of information. And recently, in late 2020, they came out with some guidelines for maintenance of bridges and basically just like prioritization and everything that has to do with bridges. It's a very thorough, very long methodology, but it's actually really good. I'm only going to focus here on this part, which is level 2, which is the definition of attention classes, which is basically their answer to a prioritization scheme. The way that it works is that it's a multi-hazard approach. So they have different kinds of hazards. For each one of the hazards, they have each one of the 3 components of risk: hazard, exposure, and vulnerability. And for each one, you're going to get a class of attention. After you get a class of attention for each one, you're going to combine everything and obtain a class of attention for the whole. The methodology actually works really well. It's actually very thorough and it's actually very robust. Now, we decided that we were only going to focus on the seismic component because that's what we do. So we decided to just do that part as the first stage, let's say. So we applied it to our case study. We basically took exactly what the guidelines are saying right now, and we applied it as is to our inventory for which we had full information. So basically we get a hazard score, an exposure score, and a vulnerability score. Once that you mix everything together, you get this. This is like your overall seismic category. Now, I don't know if you can see it very well in the monitor, but it's like 600 out of 620 bridges from the inventory were classified to the highest possible class of attention. Basically, the methodology is saying, the guidelines are saying that everything is urgent. Now, this becomes a problem, right? The methodology is a little conservative. But basically, if you have a problem right now where you don't know where to begin, you apply a methodology that tells you that everything is urgent, then you're right back at square one. You still don't know where to begin, right? So we decided to do something about this. So let's try to improve this methodology to see what we can do if we can improve this type of results. So an ideal solution would be to do average annual loss based prioritization. So this would mean that if I have my full information, the same that I was running on with before, enough information for me to calculate average annual losses for each one of the assets, then I could rank them based on average annual loss. Whoever gets the biggest one goes first, whoever gets the lowest one goes last. However, as we were talking about, they don't have enough resources. The bridge management agencies don't have enough resources to try to do this problem like this. So what we decided to do was, okay, how about if we apply a machine learning model to this situation? Now with a machine learning model, I could train it with the information that I do have from my database to try to predict the average annual losses and therefore try to predict the priority based on those average annual losses. Now, I don't have enough information for me to build a machine learning model that is going to work for any situation, right? So this is only going to work for my case study. However, I didn't want to do a machine learning model to use it in production, let's say, to actually use it on a real case, but I use it because of the machine learning framework or the data science framework, in which you have something that's called feature component analysis. So basically, if I train the model and the model works well, it can tell me, based on the features that I chose, which are characteristics of the bridge, which ones are more important, which ones have the biggest influence in terms of losses, in this case also priorities, and how do they relate to the values that the guidelines are already using. So that's what we did. So we took 6 parameters, we trained the model. The model works okay. I mean, we don't have that much information, but it works decently. But we decided to focus on this, on the parameters, right? So using this information, basically, we compared this range, or this gradient of importance, and we compared it to how the guidelines are right now giving importance to each one of these values currently in their current format. So we use the insights that we get from the data to alter the Italian guidelines. So we calibrated the values that they already do use. We included a new one that seemed to be important that they hadn't included before. Basically, it has the same ease of use. I'm using the exact same thing. The only thing is that I'm only recalibrating the values, the weights, if you may. We also eliminated the 5 categories because using only 5 categories is kind of limiting, right? If you have a big inventory of bridges, you're going to end up with a lot of bridges within one category. So we just use a score system. Instead of just limiting to 5, it can be whatever it has to be just based on the score. And this is the results that we obtained. So this is what we had before, right? Everything is saturated, everything is red. After we apply the methodology, it becomes like this. So right now, it works well. It works much better than before. I actually do have like some bridges that are in a top priority, very few elements, which I could start and go and look. If you compare this with the average annual loss based priority, you're in the range of plus minus 15–20%, which is not bad considering how easy the method is to apply. And I'm using basically the same framework that the guidelines are already using. So in conclusion, asset prioritization is urgent. It's something that we need to start paying more attention to. The current guidelines are a solid methodology, but they're very conservative. Everything gets thrown into the most urgent category. Data-driven insights, like the thing that I did here, can be used to calibrate these methodologies, and this proposal seems to provide, or it does provide, an improvement based on average annual loss as a benchmark. Finally, we're almost there. So, future developments. What else can we do from here? So, bridges worldwide, they're deteriorating, and they're deteriorating fast. This is a problem that is only going to get worse, so we need a lot more research and a lot more assessment to be done. The things that I wanted to do that I didn't have any time to apply was, okay, what happens to gravitational loads? How about if we deal that as a hazard? We need to improve the way that we do deterioration models, because this seems to be like the biggest issue. And over time, there's been an increase in the traffic loading that is going to be having an impact on the current inventory, and it's something that we haven't really discussed before. More research is necessary to fill the gap between the state-of-the-art and the standard of practice. In my opinion, if we just keep, pushing the state-of-the-art without looking at what the practitioners need, this is going to become a problem. So we need to do more things in this thing, within this topic, which are based on software development, something to bring it to the practitioners that help. Simplified fragility models. Try to think of simple research that we can do that can help bridge this gap. Indirect losses, they have a big importance and they should be included regularly, right? There's a lot of things that I didn't do. This was like a first approach meant for prioritization, but we should include something for simultaneously collapsing bridges, which would make things hazard specific. include more damage states, right? I'm only basing my information on the deterministic occurrence of collapse, but what happens if it's damaged, right? What are the assumptions that you need to make in case of, okay, what damage means what decision in terms of decision making, right? For all of this kind of stuff. We didn't really take any of that into consideration. And we need clear and efficient methods to prioritize asset in a portfolio, and this is something that we need to do more about. We only focus on the seismic part, but there is multiple hazards. I only focus on reinforced concrete bridges, but there are many different types of bridge typologies. So there is a lot more to be done within this field. And we made it.
Thank you, Andres. So we have time for questions now from the committee. I think Professor Sesov is going to start.
Thank you, Andres, for quite interesting presentation. Actually, it was so well presented that I have no question. You said no rooms. You left no rooms for questions, but still I have some doubts and questions regarding your research. So first of all, you mentioned that you also apply some kind of machine learning in order to fill the gap in exposure model for the information that you have or you don't have. But you mentioned also at the very last slide that for the bridge inventory for bridges, it's very important the maintenance that they do have during their exploitation period. So one of the things, did you apply this like a parameter of age or technical codes or the year that was constructed? Because these parameters are quite important regarding the then calculation of all this risk modeling. So it's not always the same that the bridge has been constructed 50 years ago with very bad maintenance, and if it was even strengthened or well maintained. So what do you think about this? Did you apply this in this machine learning, that you can run so many times and machine can give you some kind of answer to that?
Yeah, thank you for the question. No, we didn't include it because our database was very specific. So most of the bridges that we had, or all of the bridges that we had, were from the late 60s, 70s mostly, and late or early 80s. So it was a very specific range. And in Italy particularly, well, we actually analyzed them statistically. There seemed to be no difference in the fragility that I would get based on the year, right? There seemed to be no correlation, so it was a parameter that we left out. The issue with that is that the first code in Italy that started dealing with this on the bridge perspective was in 2003. So every bridge that was done before that, they had it wasn't very well organized in Italy. And all of the bridges were from the same decade or 2-decade period. So yeah, analyzing it statistically, there was just no correlation between it. So we just kept it out. We did consider it, but we just left it out of the models.
Okay, thank you. And the last one is that, more or less like a discussion, you mentioned that you use some of the guidelines that bridge managing authority used. Did you get any reply? Did you show the results to the agency in order to say, yes, we can improve your guidelines? And what is the feedback, or you didn't get any?
So far, no, we haven't had the time, but they just came out with a new one, right? I mean, they just came out with a new version that I still haven't seen. So, because this was kind of a recognized problem. I'm not the first one to say this, that that it's very conservative and that it's throwing everything up. So I do have to see what were the changes that were made, and we are working on some projects which are related with the people who went this. So I will get the opportunity at some point to, say something about it. But we'll see what they've done.
Okay. Thank you, thanks.
Any other questions by the committee? Yes, please.
Only one question. According to your opinion, there is some other intensive measure useful for defining the hazard for your analysis. In other words, you worked only with acceleration sensitive anyway.
Yes.
Models. Okay, there are the possibility that velocity sensitive or displacement sensitive models are intensive measures, are necessary for your analysis.
We didn't get the time to explore it, honestly. Other people have done it, and they do come up with that velocity base might be better than the other ones, right? Than the acceleration based ones. But I mean, we focused within our scope of just using average SA versus PGA, so we stayed in our lane in that case. And really, it would have been great to explore more intensity measures so that we could say something more about this, because it's a very interesting question. The thing is that the nonlinear time history campaign is very extensive, right? So that's why we only did PGA and average SA, because it took, even just with those two, it took months. So we needed to really keep it limited.
Thanks.
Questions from the audience? Oh, yes, Michele.
I knew it. I knew it was coming.
You knew what?
That it was coming.
You did an excellent presentation. So I'm more asking for comments than really to answer a question. You know that bridges in general are not that sensitive to earthquakes. If you look at how many bridges collapsed in Japan, which is an interesting region, in the last 130 years, there have been 17 bridges total, starting from the end of the 19th century. So, and if you look at what happened in Italy, you were showing collapses, but most of those collapses had nothing to do with an earthquake. So my question, or my request for a comment, is related to the fact that maybe it is more of interest rather than exploring just the vulnerability or exposure in terms of probability of collapse and therefore of completely losing a joint in your network. It could be more interesting to explore what happens when you have a reduced functionality of your network. So a bridge where, because of a problem in a joint, you have slower traffic or reduced weight or one lane instead of two, and so on and so forth, because this is much more common. Or instead of having 2 years' time, which is correct probably for reconstruction, maybe you have 1 week or 2 weeks' time, because the problem is just to substitute a bearing which is, being seriously damaged. This may change completely your conclusion and your vision of what should happen. So that's my comment.
Yeah, thank you for that. Yes, it's completely true. Actually, all of those collapses and most of the collapses that we have been seeing worldwide, they're not related to earthquakes, right? So that's kind of the sad part of me only focusing on the seismic component, because that's what we do, right? But it is true. Like, the biggest problem seems to be deterioration and gravitational loads, right? And the increase of those loads in terms of in terms of the collapse, right? But you are right. This type of analysis, like the one that I did, it could be taking into consideration the daily results, for example, so that you could identify the bridges that are more sensitive or that have the biggest impact, so that you could start taking better care of them. And even because some of the traffic information that we have is separated by times, so you could even see at which times you should close a bridge to make some maintenance. You could also see, for example, the results that I have here are meant, so I'm taking away one bridge at a time. There's something very interesting that happens. Sometimes if you take away 2 bridges, it's worse than A plus B, and sometimes it's not that bad, right? So sometimes it's good to identify simultaneously bridges that I can close at the same time that will not have that big of an effect on my network. And this all can be done with just small alterations of the same methodology that we're using here. So yeah, that's kind of the situation, but it is completely true. We need to start drifting away from the seismic part for bridges and just focus more on maintenance and this type of situation.
Okay. If there's okay, Rui, last question.
Well, again, like Michele, not really a question, just a comment, and really just an excuse for me to compliment you on your presentation.
Thank you very much.
Michele has already said I'm exaggerating, but I don't care what he says. Your work, as Michele was alluding to, it really is of a general nature, in the sense that exactly as Michele was saying, rather than considering seismic hazard, you can consider anything else to do this type of analysis. And so my question is, I would be personally surprised if something like this has not been done already or is not being used already by agencies that have the responsibility of deal with the maintenance of road networks. So my question is, have you seen, looking at other areas, if you will, risk and operability, operationality, management areas that are not related to earthquakes, have you seen a methodology like this being used?
It's surprising how much I would also think that bridge management agencies, like, they do a lot of this type of analysis, but really it's kind of disappointing the level of, like, that they basically don't. Now, I recently came across a paper from Politecnico, which uses a very similar approach for this type of situation, right? And it is true, is that all of this, well, that part for the indirect losses is completely hazard independent, so it's very useful. But yeah, I was surprised too that I didn't find anything on those lines, right? Everything, I had to learn it from the transportation agencies, like from the transportation engineering fields, but really not from the management or the bridge management institutions. They don't have the information, they don't, yeah, it's really not well.
Okay, so Andres, thank you again.